This is video 3. We present here the definitions and notations for assemblies and tile assembly system. Note that we focus here on temperature 1. A tile assembly system is made of tiles. A tile is a unit square with a glue on each of its 4 sides. We introduce now the glue label and the tile type. The set of glue labels is finite and denoted by G. In the running example of this video, we consider 30 different glue labels. On the right side, there is an example of a tile type called T2. On its north side, the glue label is G6. On its east side, the glue label is G3. On its south side, the glue label is G12, and on its west side, the glue label is G2. A tile set is made of a finite number of tile types. In this example, we consider 29 different tile types. Remark that some tiles have no glue on some of their sides. Now consider the grid graph. Please put some tiles on the grid. More formally, this placement of tiles is a partial function alpha. This function associates a tile type to each position of the grid occupied by a tile. The domain of the partial function alpha is a subset of positions of the grid graph. We represent here the subset. Let's go back to the partial function alpha. And let's focus on the tile T27. This tile is in gray. Let's zoom on this tile. Now, look at this tile and its right neighbor, the tile T20. These two tiles have the same glue label on their abuttal sides. In this case, we say that these tiles interact. We represent this interaction by an edge between these two tiles. Now focus on the tile T27 and its north neighbor, the tile 22. The glue labels on their abuttal side are different. These two tiles does not interact. In fact, a tile with no glue label on one side cannot interact with another tile on this side. Since there are no interaction, we do not draw the edge between T27 and T22. Let's zoom out. All the edges which represent an interaction between two neighboring tiles are drawn. This set of edges is called E alpha. Now we can define the binding graph of alpha. The set of positions of this graph is the domain of the partial function alpha. The set of edges of this graph is E alpha. The partial function alpha is an assembly if and only if its binding graph is connected. Almost all partial functions considered in these videos are assemblies. Now let's remove some tiles. We obtain an assembly beta. The domain of beta is a subset of the domain of alpha, and for all positions in the domain of beta, both assemblies put the same tile on this position. In this case, we say that beta is a subassembly of alpha. Now we will make beta grows. Here we attach a new tile T4 to the assembly beta. This tile is in gray. We obtain a new assembly called beta 1. Let's make beta 1 grow some more. Here is beta 2. Here is beta 3. Here is beta 4. Here is beta 5. Here is beta 6. Here is beta 7. Here is an assembly beta prime. Let's stop here for the moment and look at this assembly. First, remark that beta prime is obtained from beta by a sequence of tile attachments. In this case, we say that beta prime is producible from beta. Secondly, beta prime is no more a subassembly of alpha. Nevertheless, for any position common to the domain of beta prime and alpha, both assemblies put the same tile on this position. In this case, we say that beta prime and alpha are consistent. If two assemblies are consistent, then it's possible to make the union of these two assemblies. In this example, we represent the union of alpha and beta prime. The domain of this assembly is the union of the domain of alpha and the domain of beta prime. Nevertheless, there is a subtlety for the interactions. Look at the following edge. The edge in red represents an interaction which does not occur in alpha or in beta prime. This interaction occurs only in the union of the two assemblies. This remark is not a problem along the proofs. The more interactions there are, the easiest it is to prove that a partial function is an assembly. Nevertheless, the binding graph of the union of two assemblies is not the union of their binding graphs. Lots of subtleties occurs along the proofs. In this model, details are important. For an assembly, we use notations similar to the ones introduced for graphs. For example, lowercase x alpha represents the lowest abscess of a position which is occupied by a tile of the assembly alpha. Let's come back to assembly beta and let's make this assembly grow again. Here we attach the tile T29 to the assembly beta. We obtain an assembly beta second. The new tile is in gray. The position occupied by the new tile is occupied by the tile 27 in alpha. Thus alpha and beta are not consistent anymore. We say that they are inconsistent. If two assemblies are inconsistent, we cannot define the union of these two assemblies. Thus making the union of two assemblies requires to check beforehand that they are consistent. We can now define a tile assembly system. Such a system is made of three elements. The first one is a tiles set. In our example we use the tile set T introduced at the beginning of the video. The second element is a seed. The seed is an assembly represented by the letter sigma. This special assembly is the starting point of the system. We will grow other assemblies from this one. The seed is represented in black in our examples. Finally, the last parameter is the temperature. In these videos, we always consider temperature 1. At temperature 1, no more constraints are added. At higher temperature, the assembly have to satisfy more constraints. Check the article version for the definition of tile assembly systems at higher temperature. Remark that the assembly alpha is producible from the seed in our example. Then we say that alpha is producible by our tile assembly system. The assembly beta second is incoherent with the seed and cannot be produced by our tiling system. The set of production design all the assemblies which are producible from the seed. Among these producible assemblies we are interested into some specific ones called terminal assemblies. A terminal assembly is an assembly where no more tile can be attached. In this example, we represent an infinite terminal assembly producible by our tiling system. Let's explain the structure of this terminal assembly. On the right part, there exists a periodic infinite structure represented in gray. From this periodic structure, some periodic infinite assemblies grow. Finally, some specific positions can be occupied by one of the three tiles T27, T28, T29. These positions are in gray. Thus there exists an infinity of terminal assembly in our tile assembly system. If the set of terminal assembly contains only one terminal assembly, then the tile assembly systems is deterministic. In the article, we will only consider deterministic tile assembly system. Let's do some modifications to our current tile assembly system to obtain a deterministic one. Here is a new tile set T' where the tile T27, T28 and T29 have been fused into a unique tile T'27. The following tile assembly system is deterministic. The example shows the unique terminal assembly producible by the seed. Since the system is deterministic, the type of the tiles can be removed. Whatever way the seed grows, a position will always be occupied by the same tile type.